Hello, everyone. It's a pleasure to see you again at our UK Quantum Fluids Network webinar. And today's speaker is going to be Seth Musser, a PhD student from MIT. And he's going to talk about flying in the superfluid. So whenever you're ready, Seth.
Yeah, sure. Thank you for the very kind introduction. And thanks to Davide for the invitation. As you'll see, he was one of my co-authors on this work. So right now, I'm a graduate student at MIT in condensed matter theory. And I do things which are pretty different from this work. So I work in solid state physics, looking at some transport and topological order things. I'm just flashing this slide to kind of give you a flavor of the things I've been doing recently. That way, I apologize if I forget any of the specific details of this work. I'll do my best to remember. So please interrupt me at any time. And I'll do my best to remember the exact details of what we did. But without further ado, I kind of want to jump into flying in a superfluid and talk a little bit about why we might want to fly in a superfluid and the theory of flight that will allow us to understand how we can do that. And then I'll show some numerical data where we were able to demonstrate that it is possible to fly in a superfluid. Okay, so let me just provide some motivation, give a possible vision for why this might be useful. So superfluids are fluids without viscosity. In liquid helium, which has a superfluid component, that part will have zero viscosity, and the normal component will have some shear viscosity. So this can lead to very high Reynolds numbers, even for small length scales, which means that it's theoretically possible to have a tabletop experiment with a superfluid where you achieve Reynolds numbers which are comparable to that of a wind tunnel because of the low viscosity. And while I was preparing this talk, I figured that I would do a quick Google search to see if anyone is running an experiment like this at the moment. And there was recently a Florida State professor, and maybe some of you as well, who is building a tunnel, a wind tunnel, or rather, I guess, a superfluid tunnel to observe high Reynolds number flow. So hopefully that provides maybe a little bit of motivation for why it might be useful to think about flight in a superfluid. And without further ado, I'll kind of jump in and set the stage for what we'll be thinking about before I have some digression into the theory of flight and discuss how that applies to the superfluid. So we'll be thinking about a weakly interacting Bose gas, and we'll make the approximation that temperature is strictly zero. And what this will mean is that all of our bosons will condense into the same state so that the many-body wave function will just be a product state. So in this classic image, the formation of this condensate where all of the bosons have kind of condensed into the same state, representing this peak in the momentum distribution. And what we want to do is consider the dynamics of this wave function psi. To do that, in condensed matter theory, we'd like to think about writing down some free energy and then look at the equations of motion governed by that. So what we'll think about are these are cartoon bosons here. And they'll have some short-range contact interaction. For example, neutral atoms like neutral sodium atoms, where we can neglect long-range effects like the Coulomb interaction. And for this kind of weakly interacting superfluid, we can write down some free energy. We can find its equation of motion, which is known as the Gross-Pitaevskii equation. And empirically, this provides a pretty good description of weakly interacting superfluids like Bose-Einstein condensates. It even reproduces some of the features of helium-4, which is more strongly interacting. So here I'm just going to write down the GPE. I won't justify this, but I'll just walk through the terms. So we have our standard kinetic term that we see in the Schrödinger equation. We have some external potential. This is where we'll see a lot of the physics that we encounter later, where we'll add an external potential in the shape of an airfoil that we can drag and generate vortex nucleation. And then we have this last term, which represents a contact interaction. So this is the addition beyond just the Schrödinger equation. This is coming from the mutual repulsion of these bosons. Okay, so this is our kind of mean field description of this weakly interacting superfluid. And what we'd like to now do is reintroduce the fluid into the superfluid. So we're going to write the wave function as root rho e to the I phi. And what you see here is that if we take rho star rho, or if we take psi star psi, we'll just get rho. So we can interpret rho as the number density of the superfluid. And we'll take this vector valued function u to be the gradient of phi. And you'll see why I call it u in a little bit. So when we do this, we can transform the GPE from a single complex equation of motion into two real valued ones. This is known as the Madelung transform, and probably many of you are familiar with it. The first equation we'll get is just the conservation of particle number. So for those of you who have seen fluid mechanics or fluid dynamics, this is the exact same as a conservation of mass equation of motion. And you can see now why I indicated this vector value. I called this vector valued function u, because we can think of it as a velocity. It's entering this equation of conservation of particle number equation of motion exactly the same way the velocity does. The second equation of motion that we'll get, we have our material derivative of the velocity, and then we have these terms on the right-hand side. So these are the this is a conservation of momentum equation of motion. This first term is just coming from the repulsive pressure, this contact repulsion between the bosons. This next term is the external force due to the potential that we add. And the last term is known as the quantum pressure. So in much of my discussion, I'll neglect this term. If we were to non-dimensionalize this equation, it will turn out that this term is only relevant when the density is changing on the order of the Keeling length, which is the only length scale in this equation of motion. Okay, so I've written down the fluid equations. These probably look a lot like what you've encountered in your typical fluid dynamics class. But there's a very special property here that I want to highlight, which is that because u is the gradient of phi, where phi is this angle, the phase of our superfluid wave function, this means that the vorticity, the curl of u, is 0 almost everywhere. But because phi is multi-valued, so it can take 0 is equal to 2 pi here, we can have situations where our phi field winds by 2 pi around some point-like vortex. And as you can see, if we take the gradient of phi, this will lead to a circulation around the vortex. So our vorticity is quantized at these point-like vortices. And these are topological defects. In fact, I would say like the paradigmatic example of a topological defect. So they're stable to all kinds of perturbations. And you can really easily detect them in experiment by doing absorption imaging and looking at the zero density that they produce at their core. The second important feature here is that there's no viscosity. Indeed, when people were first thinking of superfluids, the definition was that you had this flow without loss of energy. So of course you shouldn't have viscosity even as you add additional terms to our weakly interacting Gross-Pitaevskii equation. Okay, so we have these topological defects, but how do we generate them? They may be stable once they're generated, but how do we go from a condensate which has no vortices to one that does? What was found in many numerical simulations, too many to count, I'm just showing two here, that if you take a large potential, say a Gaussian potential in the shape of a disk, so that the superfluid evacuates from it, and then you drag this potential, you'll create a flow around the disk. And for appropriate sizes and speeds of that disk, you can get vortex nucleation. So here we have two oppositely signed vortices nucleating, and you can even produce a von Karman vortex street, where you have two similar signed vortices nucleate, and then two of the opposite sign nucleate from the bottom. So by obstacle dragging, you're able to actually generate these topological defects. So that led to a natural question for us. What about flight? In this is a classic movie made, I think, in the 60s as part of some fluid dynamics education. And you have this foil which is suspended in water, and all of these particles allow you to trace the velocity. So as you drag the foil, you generate this single vortex at the back that looks a lot like our vortices in a superfluid, although of course its vorticity isn't quantized. However, you'll notice that this is a little different from these earlier situations. These had oppositely signed vortices. This is a single vortex with some distinct value, distinct sign. So this had not yet been demonstrated, but we were curious as to whether or not you could generate lift by this kind of vortex generation. Okay, and now I want to kind of jump away from superfluids and talk about the theory of flight so we can understand what might be challenging about generating lift in a superfluid and how we might go about that. What might we expect? Okay, so before we understand whether it's possible to generate lift, we need to think a little bit about the theory of flight. Obviously, lift on a wing will imply a pressure difference. We need to have a higher pressure below the wing and a lower pressure up top, and vice versa. For those of you who remember Bernoulli's theorem, the pressure plus 1/2 times the density of the fluid times its velocity squared is constant everywhere in an irrotational inviscid fluid. And what this means is the pressure difference, a higher pressure on the bottom, will mean that the fluid on the top must move faster. And just as an aside, often, certainly in the US, maybe the UK does a better job, this is given as an explanation for the generation of lift in a way that's a little incorrect. So in high school, I learned that the fluid particles, as they come over the foil, they need to meet back up at the tail of the foil. And since the fluid over the top has further to move, it has to go faster. While it is true that it goes faster in order to create this pressure difference, it isn't true that these fluid parcels meet back up, as you can see in this simulation. The parcels that move over top of the foil are slightly delayed relative to the ones on the bottom, even though they're moving faster. They don't quite move fast enough to overcome the greater distance. So I just add this just in case anyone has learned the incorrect way, this theory of flight as I did. Okay, so we know that lift on a wing means a pressure difference, and by Bernoulli's theorem, this means a velocity difference from the top to the bottom of the foil. But now if we go into the frame of the foil, this velocity difference moving faster over the top and slower over the bottom will lead to a net circulation, the integral of velocity around the foil. And there's a theorem that you can prove in inviscid irrotational fluids, the Kutta-Joukowski theorem, that says lift is proportional to this circulation. So what we've learned is that creating a circulation will necessarily create lift, and lift necessarily requires a circulation around the foil. You might ask, why discuss circulation? Why not focus on this pressure difference? And the reason is that as physicists, we really like conserved quantities because they make our lives easy. And circulation happens to be a conserved quantity in a two-dimensional fluid. So we can express the circulation as some integral over the vorticity, over the region bounded by a curve. This should hint to you that it might be a useful thing in superfluids as well, where this vorticity is quantized at point-like vortices. But even outside of the superfluid context, in an incompressible inviscid fluid in 2 dimensions, vorticity is just advected with the flow. And this means that the circulation around a loop will never change as long as that you allow that loop to be deformed by the fluid. So this already helps us to understand some of the dynamics of generating lift around an airfoil. We know initially this airfoil will be at rest and thus have 0 circulation, which means that this loop A, B, C, D must have 0 circulation. When we accelerate the foil, empirically we know that there's lift, and that means the foil must have some circulation around this loop, A, E, C, D. But conservation means there must be an equal and opposite circulation in this last loop here. So there must be some kind of a vortex with equal and opposite circulation of the foil. So already, just by this understanding that lift is linked to circulation and the conservation, we've realized that there must be this starting vortex. And I'll play this movie again. So as we drag the foil, we see that there's a starting vortex. And we can now understand this starting vortex as kind of being directly responsible for the lift that the foil feels. Okay, so now we want to think about how do we actually choose the specific value of lift? Because it may be the case that we could choose any circulation. Like, how does nature pick a circulation, basically? So for that, we need a little bit more, to be a little bit more careful and exact. So we'll need to find the flow around the airfoil. And let me just specify to the most reductive case. An irrotational, so the curl of the fluid is 0, and an incompressible, so its divergence is 0 as well. These 2 facts mean that I can write a potential function for the velocity, which is an analytic function of the complex x plus iy coordinate. This might seem like a little, like an unnecessary amount of math, but it will prove very useful because it will allow us to use a special conformal transformation to figure out the flow around a foil. And then we'll be able to understand why nature picks a specific circulation. So we can write down almost immediately the flow around a disk. There's this potential here, which produces a velocity field that is parallel to the x-axis at speed u, capital U, and which does not penetrate some disk. So we get this flow around a disk right away. We can further superimpose a point vortex inside of the disk, allowing for an arbitrary circulation around it. So the streamlines here at 0 circulation, they'll just come exactly parallel to the x-axis. And at some finite circulation, they'll curve around the disk. Okay, so we've done a simple solution around a disk. But now we can actually map the flow around the disk to the flow around an airfoil. There's this, you'll hear the name Joukowski a lot because he did a lot of seminal work here. This conformal map is known as the Joukowski map. And it will map streamlines around the disk to streamlines around the airfoil here. And this allows for a complete solution of the flow up to the ambiguity that we can have any circulation around the foil. So how do we pick this circulation? We want to avoid a diverging velocity. So when we pull the foil and we peel off this starting vortex, why does it have the given circulation that gives the foil lift? It's because nature wants to avoid an infinite velocity at the tail of the foil. So I'll just show some streamlines around the foil with no circulation. We have this stagnation point at the front of the foil where the velocity is 0, and another on the back side of the foil. But you can see that as the fluid comes around this infinitely sharp point, it has to very quickly move around that point. And in fact, there's an infinite velocity exactly at that tail. And this is true for all values of the circulation, except for the Kutta-Joukowski circulation, which causes the stagnation point to be exactly on the tail. So this particular value of gamma is proportional to the speed of the foil, its length, and the sine of its angle of attack. And by that earlier theorem, we get a lift, which is proportional to rho u squared L sine alpha. Okay. So let me just review this kind of building up of the theory of flight. We saw that circulation around a wing implies lift and vice versa. And we saw that we actually get this circulation by emitting an equal and opposite starting vortex. And the value that that starting vortex has, the value of gamma, is chosen to avoid velocity divergence at the tail of the foil. And I'll just note, every single step of this reasoning can apply to a superfluid. As long as we're away from any large density variations, we can treat the superfluid as nearly incompressible. And it's already irrotational and inviscid. So all of the approximations I've made will carry through, and we can apply this reasoning. However, there's one crucial fact which I haven't touched on, and it's this initial transient. So when we start the foil, it has 0 circulation before it emits a starting vortex. And so the natural question is, what actually causes the emission of that starting vortex? And that's where we'll see a big difference in standard viscous fluid versus a superfluid. Okay, so how do we actually get this starting vortex? So there's a bit of history in Atchison's Elementary Fluid Dynamics, which, by the way, is an excellent textbook. Many of my figures are from this book. So if you want to learn more about the theory of flight, this is absolutely the one I'd recommend. But there was some interesting history that I was reading. It was actually thought initially that this infinite velocity around the tail when the circulation was 0 would lead to cavitation bubbles because of the large velocity would lead to a negative pressure. And these cavitation bubbles could allow the vortex to separate. So this type of mechanism doesn't have to be restricted to air or water, but could occur in a superfluid as well. However, in 1904, it was realized that this actually isn't what's happening. Instead, viscosity plays a crucial role. So in almost all of my discussion, I was assuming that our fluid was inviscid, no viscosity. And that's true almost everywhere in the fluid, but near the surface of our airfoil, it's not true because there's a no-slip condition. And this no-slip condition says the value of velocity at the surface of the foil needs to be 0. So there's a region where it interpolates from 0 to the value it'll take away from the foil. And in this region, viscosity plays a really important role, this boundary layer. So viscosity is important at the boundary layer around the foil. And there's an important dynamical effect that this boundary layer undergoes. So let's think about the foil as we just start to pull it with no circulation. We'll have an incredibly large velocity at the tail of the foil, which will lead to a very small pressure. And over here, as we turn the corner, the pressure will be larger because the velocity is smaller. So an element of fluid following this streamline will have to climb from this very small pressure to a much higher pressure along the streamline. Because the velocities are so small within the boundary layer, this adverse pressure gradient will lead to a reversed flow. So we'll actually start to set up a starting vortex that is pinned to the foil at very, very short times after we start dragging it. And eventually that adverse pressure gradient will pull off this starting vortex boundary layer into the starting vortex well separated from the foil, and we'll get the lift that we know we have to get. There's finally one other important effect of boundary layers, which is that if the angle of attack of the foil gets too large, we will get separation of the boundary layer, which you can see here from these streamlines on the backside of the foil as well. And that will just lead to vanishing circulation and destroy the lift. So this is what's known as stalling in if you're a pilot flying in air. Okay. So let me just do a final review of the theory of flight. We've learned that viscosity plays a crucial role. In order to get lift, we have to get circulation. In order to get circulation, we have to emit starting vortex. But in order to actually emit that starting vortex, we need to set up a boundary layer and have this pressure gradient pull it off. Okay. So how might this work in a superfluid? Obviously, we're not going to have a boundary layer because we no longer have, or at least if we have a boundary layer, it won't be the typical boundary layer because we no longer have any viscosity. However, I showed you some numerical simulations earlier that displayed vortex shedding in a superfluid. So we saw some flow around a disk, which was nucleating vortices. So you might ask, if there's no boundary layer, how did that happen in the superfluid? Well, there's been a lot of numerical work which has shown that nucleation at a given point R can be expected to occur whenever the local speed at that point exceeds the local speed of sound in the superfluid. So in a fluid like air, this will lead to some shock formation. And you're actually able to see this in some passenger jets. As you come down for a landing, the flow over the engine may be slightly greater than the flow of sound, which leads to a gradient in the density that you can see through the refraction of light. So you can actually see the formation of these shock waves where there's some local exceeding of the speed of sound, even if the entire plane is not exceeding the speed of sound. In a superfluid, though, rather than leading to a shock wave, this tends to lead to vortices. Okay, so let's now register a hypothesis. We'll guess that this velocity criteria plays the role of governing what actually leads to emission of our starting vortex. Although, because vorticity is quantized rather than a starting vortex, we may have emission of several, which leads to the same circulation. So we can guess that our circulation will be approximately the Kutta-Joukowski circulation to avoid that velocity divergence at the tail. But it will now occur because we don't want to exceed the local speed of sound rather than because of boundary layer effects. Okay, so going into our numerics with this hypothesis, I'll now discuss what we found numerically. So we simulated the GPE with a foil-shaped external potential that we accelerated from rest to some terminal velocity. So you can see here a density map of this foil where the density of the superfluid is very nearly zero inside the foil because of the external potential. The length of the foil is L, its angle of attack is alpha, and its speed is U. I'll mention here, our characteristic length is the healing length, which is roughly the size of one of these quantized vortices, as you can see here. And we performed these simulations in a confining box, which was 1,024 healing lengths by 1,024 healing lengths. The foil sizes were around 100 to 300 healing lengths. And we did indeed observe nucleation of vortices from the tail of the foil. So here I've highlighted them with red dots to make them easier to see. You can see them either as density depletions in the density field, or you can see the phase winding around the vortices in the phase field. And you'll note that if we look around this foil here, we have a phase winding of 6 pi, which corresponds to our 3 equally signed vortices that we've emitted. So let me show a movie of a simulation that we performed. Here we were dragging the foil at 26% of the speed of sound in the superfluid, and its length was 325 healing lengths. And its angle of attack is 15 degrees. Okay, so as we start to drag this foil, we emit a small vortex, which you can see in the density field. We've now reached our steady state velocity. We emit a second vortex, and at this point, the foil has equilibrated, so we don't nucleate again. You can also see some features here. There's an initial density wave, which as we accelerate the foil, we'll see that this will lead to some features in our lift and drag plot. But for now, we'll just focus on the vortices that we nucleate because we know that that's a good proxy for lift. There's one more phenomenon that we were able to observe. So now we'll take a smaller foil moving faster, nearly 35% the speed of sound. And we see that we emit 1, 2, and we'll soon emit 3 equally signed vortices. And as soon as we emit that third, we'll start emitting vortices from the top of the foil and continue to do so uncontrollably. And I'll play this again. In our paper, we dubbed this behavior quantum stalling because it's very analogous to the separation of the boundary layer from the foil in the classical case. There, we have some circulation, which is lost as the boundary layer separates from the foil. Here, we're nucleating oppositely signed vortices from those at the tail, which is reducing the circulation around the foil. So we would expect to be stalling in this regime. We made a plot of foils. This is all angle of attack 15 degrees. So various lengths of the foils and various final velocities. My initial movie where we nucleated 2, you can see is this point. So this corresponds to 2 vortices nucleated from the tail. And when we nucleated 3, this corresponds to this red point. And the octagon indicates that we were nucleating from the top. So we're marking that we're nucleating from the top. Okay. And I mentioned that we predicted nucleation would occur when our local speed exceeded the speed of sound. And what we'll do is we'll just take the ideal flow speed around that Joukowski foil with the conformal map I showed, and we'll predict nucleation whenever that local speed is greater than the speed of sound at some cutoff away from the foil. So because this ideal velocity is infinite at the tail, we'll need to introduce some cutoff. So we pick a value which makes our fit the best. And we see that we get really good agreement with our data. This orange region here is where we predict that we'll need to nucleate 1 vortex from the tail in order to avoid the velocity at the tail being large enough that it's larger than the local speed of sound. You can see that in every one of these regions, we have pretty close agreement from the actual observed number of vortices we nucleate. And we additionally, this white region, predict that we'll nucleate from the top whenever the velocity at the top of the foil, once we're done nucleating from the back, exceeds the local speed of sound. So we have somewhat good agreement here. It's a little less good, which we attribute to there not being a diverging velocity at the top. So there's less of a qualitative exceeding of this bound and more of just some quantitative agreement. Okay. Further, we were able to make some analytical arguments. So if we let nkg be the number of vortices we'd expect to nucleate to exactly get the Kutta-Joukowski circulation, which may or may not be an integer, and we subtract off the number that we observe and look at this difference squared, we were able to analytically show that this should scale with the length of the foil. And indeed, we found really good agreement with that relationship with a single fitting parameter, which is the slope. And when we made that plot, that agreed very well with our data also. Okay, so thus far, this is kind of all quantitative disagreements with the viscous fluid. In both cases, we get nearly the Kutta-Joukowski circulation. In the superfluid case, we do it via a series of vortex emissions because we have quantized vorticity. So that's one perhaps qualitative difference. But this mechanism, whether it's boundary layer separation or whether it's exceeding the speed of sound, is kind of more of a qualitative difference. However, there is actually a large there's a large qualitative difference with the viscous fluid. And that's in the case of stall, where we observe this quantum stall. So in a standard viscous fluid, stall is a function almost entirely of angle of attack. So my co-author, William Irvine, is a recreational pilot, and he told me that one of the first things you learn as a recreational pilot is that if you go and you notice that you're losing lift, you're starting to stall, often amateur pilots will make the mistake of trying to reduce their speed because they think they've gone too fast, and that's caused the stall. But speed has very little, if any, relationship with stall. Instead, it's almost all about the angle of attack. So you have to learn that when you're flying, if you stall, you need to dip the nose of your plane down rather than reduce your speed. And I'm showing this video so you can see that as the angle of attack is changed, that's what's really leading to stall and boundary layer separation. But of course, in a superfluid, what we proposed is that the reason that we quantum stall is because we nucleate from the top of the foil. So hold on, let me go back here. So in a superfluid, we propose that we stall because our speed is greater than the local speed of sound at the top of the foil. So in principle, it would be possible to go slow enough that we no longer nucleate from the top of the foil, regardless of the angle of attack. So here I show a plot in a standard viscous fluid of lift versus angle of attack. Around 15 degrees, you will start to stall no matter your speed. In a superfluid, we found that we could fly at an angle of attack of 30 degrees if our foil speed was low enough. And this is because keeping the foil speed low kept the speed at the top low enough to avoid exceeding the local speed of sound. So there's this qualitative difference with a viscous fluid. Okay, so finally, to finish off, I discussed a lot about how lift was linked to circulation, and I showed how we could controllably generate circulation by nucleating vortices from a foil. So obviously, what you should ask is, does this actually generate lift? And I made a plot of lift versus and drag in a simulation. Lift is this dotted line and drag is the solid line. They're obtained by integrating the stress energy tensor around the orange and green contours respectively. And what you would expect is once we nucleate a vortex, we increase the circulation of the foil by a quantized amount. So our lift should jump by a quantized amount. Instead, what we saw is we have these two large spikes. And what that was due to was that density wave that comes off of the foil when we accelerate that. And I'll show a video of this so you can see dynamically how that's happening. So this provides a bit of a challenge, but we developed a way to identify the sound waves in the fluid and remove those. Once we removed the sound waves, we got back the quantized lift we expected. So if an experimentalist were to perform this experiment, it would be a good idea to do it in a large tank, large enough that this transient sound wave doesn't reflect and interfere with the appropriate value of lift. And again, this piece here is because the foil is approaching the edge of a box. So a lot of this should be understood as finite size effects that would be rectified with a larger simulation. But because we didn't have the computational resources, we used this mathematical technique to remove sound. Okay, so I'll play this video here. You can see this density variation peel off the foil. As it returns, you'll see the lift spike up again before falling. And once the foil approaches the edge of the box and all of these waves are reflected, the lift will again increase. So if you're able to do it in a large enough box, we'd expect exactly quantized lift. Okay, so let me just finish off with whether or not this is experimentally reasonable. I believe that it is. Pretty recently, a von Karman vortex street was predicted using GPE simulations. And in 2016, it was observed in a Bose-Einstein condensate. So this same optical obstacle, which is creating a potential by use of a laser, was dragged, and then using absorption imaging, you could see the density profiles of the vortices, which allowed the experimentalists to determine that they had produced a von Karman vortex street. So if you would drag an asymmetric laser, you might be able to controllably generate one sign of a vortex and thus get lift. And that would get you closer to realizing in a lab the dream of flight in a superfluid, which we demonstrated numerically can happen. With that, I'd like to thank my collaborators, Davide, who's here, Miguel Honorado, and William Irvine. And I'll note that I was sponsored by RU funding at the University of Chicago when I did this work. And I'll open it up to your questions.
Yeah, thanks a lot, Seth. It's very illuminating talk about both superfluids and flights in the normal fluids as well. So I have a question from Toshiaki Kanai.
Sure.
Hi, thank you for the talk. About the Gross-Pitaevskii calculation, do you have the phase profile? I mean, do you have any video of the phase profile? I want to see the velocity field or however.
Yeah, of course. So let me minimize my I think I included it in an earlier version of this talk that I gave. So here we can watch that vortex peel off, and you can see the phase gradient around the phase winding around these vortices. So I can go back and play this again. You'll see pop, there comes the vortex with its 2 pi phase winding.
Nice.
Yeah, so at least around the vortices, it's straightforward to go from the phase to the flow profile. It's almost entirely circulating around the vortices. It's a little less straightforward to see the phase and understand what the flow will look like around the foil. But we found it almost exactly agreed with ideal theory.
Also, which kind of boundary condition did you apply?
Yeah, we had a confining potential, which was some box with Gaussian smooth walls. So that allowed for sound waves to reflect off of the box. If you would instead maybe include a boundary region which damped the sound waves, that might eliminate some of the numerical difficulties we saw.
Hi.
Yeah,
Thank you.
great question. Thank you.
Yeah, thanks, Toshiaki. I think it's Yuri. He's next.
Yeah, well, thank you very much, but that was very interesting.
Yeah, of course.
Could you comment? Yeah, do you hear me? Yeah.
Yeah.
Could you comment on the nature of the drag force?
Yeah, of course. So we would expect if there are no large sound waves that the drag force on the foil may be 0. This is just assuming that the superfluid very closely resembles ideal theory, where it's nearly incompressible and inviscid. But I think there was some early papers that thought about the drag force arising from some buoyancy effect, where you're dragging some potential, this potential kind of analogous to how you might drag a balloon through water might lead to some drag. But because we're considering our experimentalists are just dragging a laser manually, they probably wouldn't observe this kind of buoyancy drag force that people had mentioned.
So in short, all you can think about now is that this is related to the compressibility effects.
Yeah, that absolutely. Great. Yeah, that's a better rephrasing.
Yeah. Okay, thank you. Thank you.
Yeah, well, I can see that the drag actually gets negative at some point.
Yeah, so I chose a sign of the drag so that it was negative. So positive drag here would be pushing the foil forward. This is just to make it easier to visualize the graph so that we don't have competing lift and drag lines.
Yeah, but then so if you remove sound, so the plot on the right.
Oh, yes, yes, you're right. If you remove sound, indeed, there are these, when you emit a vortex, there are these transients where the drag suddenly fluctuates. The reason for this is that there's a large density variation around the vortex. And this, because of compressibility effects, will lead to some funny business with drag.
Okay. But yeah, it looks like it's a lot smaller than the lift. Yeah.
Yeah, yeah.
So next question is Latik.
Yeah, good evening. Thank you very much for an interesting talk. I really enjoyed. But I'm an experimentalist and our group is an experimental group. So I may only mention that Marco Lamantia here in Prague is actually performing experiments which are pretty similar. And he's able
awesome.
he's able to visualize startup vortices, and it will be published soon. But I leave that to him to explain everything because I'm not directly involved in this experiment. But let me add a few comments from the experimental point of view.
Yeah,
I
of
mean,
course.
what you have done, it's beautiful. But on the other hand, I mean, you actually assume intrinsic vortex nucleation. And in helium-4, this will never work like this. So if you have kind of a macroscopic airfoil or anything like that, then the vortex nucleation, which will happen there, that will be of extrinsic kind of nature. So it is known that the critical velocity for vortex nucleation is rather centimeters per second, rather than 1/3 of the speed of sound. So what you have done is perfectly okay, but for these kind of ideal conditions, which are defined by your equations. But in practice, I am afraid that the things will be much more complicated. Probably
Yeah.
I will stop here. Thank you.
As long as there's some critical velocity, you could redo our analysis with that critical velocity rather than the speed of sound. But yeah, indeed, I would expect certainly helium-4 also has a normal component if it's not at 0 temperature. So there is some viscous effects there. But yeah, thank you for your comment. Really cool to hear that there's an experimentalist.
Can I just add something very, very briefly?
Yeah, of course.
I think it's relevant to what Vladek said, because in real experimental conditions, well, the experiment will be 3D rather than 2D. And so
Yes,
inevitably you will have vortices pinned to the surface.
absolutely.
And that's changed a lot.
Yeah, yes. Yeah, so a much more accurate theory here would involve a finite wing. And because of the conservation of circulation, this would have, as you say, led to pin vortices, these wingtip vortices.
Yeah.
And then there'd be some downwash behind the foil. Yeah, so that would be really interesting to simulate the full 3-dimensional GPE and see what happens there.
Oh.
But
Well.
a challenging thing which I did not do because we didn't have the computational resources.
Good luck.
Okay, so we have another question from Barre.
Great, thank you. Thank you, Seth. Very cool stuff. Picking up on this thing concerning the limited computational resources, if you limit yourself to a rectangular lattice with a x-axis that is much greater than y-axis, do you get significant disruption from sound waves?
Ah, yes. So great question. What we actually found, so there's another piece of the theory of flight, which is known as the ground effect. So essentially, if you're flying a foil near the ground, where you know the velocity has to be 0, you can think of this as being due to an image foil reflected on the other side of the ground. So velocity is actually increased near the tail. So what we tried initially was narrow channel simulations. And we found that because of the ground effect, this increased the velocity around the foil. And it meant that we almost always were in the quantum stall regime because we were increasing the velocity near the top. So in order to avoid that, we chose this larger.
I see.
But if I were to redo this, I know some people are clever and are able to do a boundary region where they damp sound waves. If they did that, and perhaps put it on a cylinder or something, so that there's not this ground effect, and then chose a very long cylinder, then maybe you could avoid some of these boundary effects.
Right. I see. And quick follow-up, since we do simulations with fermions, what's your ratio wing size to area of the lattice? So maybe we can give it a try in different environments.
Yeah. So I think our lattice spacing was about half a healing length, and our wing size was on the order of 200. So it's about 400 times the lattice spacing.
Okay.
Oil size.
Okay, thank you.
Yeah, thanks. So next is Sully.
All right. Thank you for a very interesting talk. I was going to ask a stupid question, potentially.
Well,
Now,
I'll be able to answer it.
I understand that this nearly infinitely sharp rear end of your foil is theoretically very handy, but what happens if you round it? Make it more like the front edge, for example.
Yeah. So for small rounding, this will indeed, you'll no longer have an infinite velocity, but it will still be very large. And it'll be large enough that when you have a boundary layer or exceeding a critical velocity, either in a viscous fluid or a superfluid, you'll nucleate some starting vortices. So when you round it, if you round it sufficiently, so maybe consider like an ellipse that you drag, so the back is as round as the front, then you may remove the starting vortex entirely. But for a small amount of rounding, it's not enough. It doesn't decrease the velocity enough to really get rid of it.
All right, thanks.
Yeah, good question, though. Thank you.
All right, so are there any more questions? Yeah, so I don't see any more raised hands. So thanks a lot, Seth, for being with us for this webinar. And
Thank you.
I'm pretty sure that your work will inspire some experimentalists as well as theorists. So it's
That's the dream.
Yeah, that's really, really, really nice work. So yeah, thanks a lot, everyone, for being with us. And soon we will and in a couple of weeks, we'll have another talk. And we'll also upload this talk on YouTube so you can rewatch your favorite moments of this talk. Yeah, thanks. And thanks, everyone. And thanks, Seth, and enjoy your lunch.
Yeah, thank you.
Thanks.
Enjoy your evening, guys. People in the UK, I guess.